Hyperparameter tuning is an important part of your machine learning workflow. Once you have your model, you need to tune the parameters to get the optimal results. So hyperparameter tuning just means that when you create a model and the model is doing its work, it has certain parameters that can be tweaked, and that parameter will affect how the model performs. So you can tweak those parameters, and based on your data, based on the techniques that you're using, you might get better results with certain combination of those parameters. How do we do this? Well, this is kind of a unique thing about machine learning is in all of the computer science, you have your science and you have your algorithms that you implement this and it kind of go into this. In machine learning, there's no deterministic way to determine that given this set of data distribution, given this set of features, tell me what is the optimal number of parameters, optimal value for each parameters. You just have to find it. So you'll have to find all possible values of those parameters and say, can I try different things and find the combination that works the best? And so, for example, if you want to find what's the ideal number of trees in my random forest algorithm, depending on your data, depending on the features that you have, the trees that work for you might be different than the trees that might work for somebody else with a different data set. So you'll just have to find one that works best for your data set. So you just have to do a bunch of tests and find what works. So again, I just came across this really funny quote on Twitter where it says, just by changing random stuff and seeing what works is considered a bad practice. But in machine learning, that's the entire field, right? The entire field of machine learning is just test everything and pick the one that works best, right? And the trick that we will learn is how to do this systematically so that you can do this using code. You don't want to just sit and tweak the parameters manually. We'll learn this method called grid search method. This is most commonly used method for hyperparameter tuning, where you say, I will define a valid range for each parameter. Let's say number of trees. Maybe 10 trees is the minimum, 500 trees is the maximum. So you define range, what is the valid range for each parameter, and then you try every value in between those. So I'll say I have my model, I'll take my data, I'll train it using this value of the parameter, test it against my validation data, check the accuracy, and say, okay, with 10 trees, I got my accuracy as 95%. With 20 trees, I got it at 96%. So you just train a model, test your accuracy, train your model, test your accuracy. And you do this for all combinations and pick the combination that works the best. We'll see this in code. The script is in your supplement. Let's review that script now. Let's go through this hyperparameter tuning script. We've done our classification as usual. We use the training fraction, and now we have the validation fraction. One of the things you can do with all the classifiers in Earth Engine is once you have a classifier that is trained, you can call this function called .explain. So let's see what this function gives us. If I run this function, it'll give us an output. This function gives you more information about the training of your classifier. So once the classifier is trained, remember we have built some trees. In this case, we just started with the 50 trees. So we have trained our random forest model. It's got 50 decision trees that are doing the work for classifying. Using this explain method, you are able to look inside and see the actual trees that were trained. This is useful for debugging, for understanding and stuff. While it's also doing the training, random forest can also say, depending on what parameters are most commonly used. So for example, you have 10 input features that you're using. You have the bands and NDVI and other indices. And by training the different trees, and it says, I determined that based on the training that we went through, that NDVI was the most important one. So you get a sense of feature importance based on this training. So you can also use this to say, I have all this, 40 bands. Which ones are the most important ones? And you can look at that. So once you call classifier.explain, it'll say, oh, here are your trees. So you can see, when you expand these trees, you will actually see this tree. So this is the first tree, 136 nodes. This is how you read this output. You start at the top with mNDWI and say, if nMDWI is less than 0.395, then class is 2. If it's greater than this, class is 2. If it's less than this, check NDWI. If it's NDWI is less than this, do this. right? So this is the actual tree that it has built. So this is tree number 1. We go down, this is tree number 2, and you have all the different trees. So you can actually see what algorithm resulted in the different trees. And remember, all the trees are initialized with the random values. So if you just run it in a different browser or somebody else, the exact trees might be different, but overall the pattern would be something similar. And using that, it'll also give you this importance. This is the relative importance of different features. And the higher the value, the more important the feature is. So in this case, when we learned this, it says, oh, MNDWI always comes first at the root node, right? You always saw that, what determines the first split is MNDWI or NDVI. And that's why those parameters are most important to determine the final class. So now say, okay, I have all these bands. Maybe this ones I can skip NDVI, it's not really useful. Or I can skip B1, it's not really helping my model much. So this will also help you with determining what features are important. Here, there's some code here, which creates a nice chart. So you can kind of visually see that. It just kind of makes them all on as percentage. So you get a chart like this. So this is the percentage important. So you can say MNDWI is 9.2% important. So it normalizes this to 100%, and you can see the chart like this. So again, this is good for your documentation, your paper. If you just want a chart like this for the features, you can use that. Let's learn about hyperparameter tuning. How do we do this? So first, let's just see how we can tune just one parameter. This is useful to kind of understand the code and then have a code tune multiple parameters together. We want to tune this number of trees parameter. So we'll say, we'll try all possible trees from 10 to 150 at 10 interval. So here is my list of trees. So we're going to build a random forest model with our data for 10 trees, 20 trees, 30 trees, and so on. So we're going to run this classification process 15 times. And each time when we run, so we have written a function that we can map over the number of trees. So we have a list of trees, we're mapping a function. This function takes number of trees, creates a classifier with that number of trees. Here we're not hard coding it. Remember in the earlier one, we just used 50 as a placeholder. Here we say, let's build a random forest model with the number of trees that was supplied to us, train the classifier using my training data set, test it using the test fraction, so using the validation data, and compute the error matrix and compute the accuracy. So for each number of tree, we get the accuracy, and it'll run this 15 times. And once it runs, you get a chart like this. So this is the output of the hyperparameter tuning. It says, I tried all number of trees from 10 to 150, and I checked the accuracy for each model. And you can see for 140 trees, we got the highest accuracy. So we've now tuned this parameter, saying that for this particular data set and this model, let's use 140 trees, and we'll get the highest accuracy. Most machine learning systems or libraries that you might have used has this built in. So in Python, scikit-learn has this built in. You can do a grid search and it'll just give you those output automatically. In Earth Engine, there was no built-in thing, so I ended up writing this code. It's available in a supplement, and you can try this. We can now tune multiple parameters together. So if I look at the documentation, let's look at the random forest documentation. There are so many parameters. Number of trees is one, but you have other things: variables per split, min population, back fraction, max nodes, and so on. Read the documentation from the SMILE library to understand what each feature does. They are pretty standard across all random forest implementation. But let's say we want to tune this parameter, back fraction. Remember how random forest works? Every time it's training a tree, it'll take randomly some training samples and train a tree. For the second tree, it'll take another random sample and train the tree. Each tree is trained on a random subset of that. How many of my total samples it'll take for this random training? The default value is 50%. So if I had 1,000 training samples, it'll take 500 random samples and train the first tree, 500 random samples for the second tree, and so on. But is 50% the best? What about 70-30? Can I make this 0.7? Can I make it 0.1? What's the ideal value? Now, if you tune this, the number of trees might be different. It might be the number of 20 trees with 0.5 works best, or 30 trees with 0.4 works the best. So we need to tune them together. So it's just another map function. So here we say, I want to try all back fractions from 0 to 1, 0.1 to 0.9 at 0.1 interval. So I'll try 0.1, 0.2, 0.3, all the way to 0.9. I'll try all trees from 10 to 150. And we map a function on number of trees. We map a function on list of back fractions. And now we say, I'll create a random forest classifier with the number of trees and number of the back fraction that was supplied to us for the function. So in the first iteration, say 10 trees, 0.1 back fraction. In the second iteration, say 10 trees, 0.2 back fraction. And we'll keep doing this for all combinations. And again, we train the classifier, compute the accuracy, and return that. Now, this computation is too large for it to finish. Already we are doing not just one classification, but likely the 30 or 40 or 300 iterations of my classification. So you possibly, if you try to print it, it'll time out. But we learned that when something times out, you can just export that. So in this case, you can just say, I have my feature collection that is output of my tuning. I'll just export that as a CSV. And once we export this, you'll get a CSV file. Let me show you what the CSV file looks like. So you'll get a file like this. You can see it says back fraction 0.1, trees 10, accuracy 94%. And you can see now the result of all the tuning. And there are, I don't know how many rows, 136 rows. So now you would say, pick the combination that results in the highest accuracy, sort by column B, and then pick the one that works best. For example, if this was the highest accuracy, you say 0.7 back fraction with 140 trees gives you the highest accuracy. And now you tune those two parameters, and you just plug them in your model and run your classification, export your final result. You are guaranteed to have the highest accuracy that is possible by this two combination. One of the things that you should be very careful about is not to obsess with the accuracy number. Because remember, the accuracy is being tested only at those validation points. It is not being tested at every pixel. So you might do all of this and suddenly you say, oh, my classification looks really bad. Because only at those 10 points that I checked, it's perfect, but everything else is really bad. So I would say do both, do this, all of this, plus do a visual assessment. And once you or a client is happy, saying that this is my classification result that looks good, and you can do this. At some point, like now, it took a while for me to develop all the code and everything, but nowadays it's there. So I just, nowadays, when I'm working on classification, copy, paste, run, and export. And I go to bed and my tuning is done. I don't really worry about how it is done, right? You just do it as part of the process, but it's not that big a problem to do it. But again, keep this in mind, don't obsess over accuracy, do a visual assessment, and then that'll give you an idea of how good you are.